This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Which are specifically the regions of stability depending on if S11 or S22 are less than or greater than 1. In the first case, we said, well, let's look at the situation where the magnitude of S11 is less than 1, and essentially what we said was that the region of instability was essentially the region of which the stability circle intersected with the Smith chart. So this region in here, if you've got S11 less than 1, this region in here is the region of instability. And I fumbled a little bit last time in describing the region of stability, which was the Smith chart minus this region is the region of stability, right? So therefore, you think of your universe being, the Smith chart, anything outside the stability circle is stable, anything that intersects between the stability circle and the Smith chart is unstable. So we worked out that region. Likewise, if we had SII, which is S11 or S22, being greater than 1, what we said was essentially that the region of stability was the part of the Smith chart where the circle, the stability circle, intersected the Smith chart. So essentially, in this particular case, the region of stability, not instability, in this case it's instability, in this case it's stability, is this particular region. Okay? And then what we did is we went through a couple of examples where we drew or determined, essentially delta, kappa. Since kappa is not greater than 1 system is not unconditionally stable, we worked out the center and the radius for each one of these, and I believe I had also made a mistake on this Smith chart. This location, this region needed to be down here because I inadvertently plotted positive 68 degrees rather than minus 68 degrees, right? So here were the two regions of instability. So one's here, the other one, this is supposed to be minus 68 degrees rather than, right, so it should be down here rather than up here. So I've made a mistake there, right? So then we continued, did another example, again just to continue with the analysis and just look at the stability circles, and we showed again the two regions of stability, and just to make sure it was CS, yep. So we've now corrected that. So therefore, the CSRS, which is the source and the center of the source circle and the center of the load circle, appropriately are defined by S11, being less than 1, S22 being less than 1, and this tells us which part of the circle is the stable or unstable region. Okay, so far what we've done is we've learnt about stability circles. We know when a particular single stage transistor is stable. So the next thing that we're going to move on to is start looking at gain, right? So far we've said, hey, we've got a transistor. Somebody gave us a transistor. We've biased it. We've got specific characteristics. This particular transistor has a given set of scattering parameters. We're able to determine if that transistor is stable or not stable. We can actually work out the regions of stability. And now what we're going to do is, the reason why we're doing, in many cases doing that, is because we want to use that transistor as an amplifier. So what we're going to do now is actually go through the process of working out gain circles, or what the gain of that particular single stage transistor is. Right? So the first thing I wanted to do in introducing these constant gain circles was, let's now talk about a special case, right? And what we're going to do is, this special case that we're going to talk about is when S12 is equal to 0. And we usually, when we're talking about a transistor and we're saying that S12 or a network, and we say S12 is equal to 0, it's got a name, and it's called a unilateral network or a unilateral transistor. But what does that mean? Yep?
It's like there's nothing that goes through the transistor?
No. Think about it. You're close, but you've left something out which has made me say no. All right? Does that mean S21 is 0? S12 is 0, which means the reversal reflection coefficient or the reverse transmission coefficient is 0. So nothing goes backwards from the transistor. So you can, and that's what's important, right? So essentially, we're going to look at doing the analysis under circumstances where either S12 is equal to 0, or we can neglect S12. And what we'll do is we'll go through the analysis, assuming S12 is 0, and then what I'll do is I'll go through and explain to you, or at least show you a test that you can do which allows you to determine if you can ignore S12 and use this unilateral assumption. Right? Because why, other than S12 not being 0, what's the significance of that? I mean, yes, you get a reflected coefficient, but if we look at these two formulae, I should say, and gamma in is equal to gamma source, right? If we're doing a conjugate match, gamma in is equal to gamma source conjugate, right? And we'll go through that in a little bit more detail. And gamma out is equal to gamma load conjugate. What do we see? We see an interrelationship, or at least a coupling between the load impedance that you need to choose and the optimum source impedance. And likewise, the optimal load impedance depends on the source impedance, right? If you didn't have that unilateral assumption, right? So what I'm essentially saying is, if we were trying to do a conjugate match, and we were trying to work out what the maximum gain is, I've gone ahead of myself. I'll say this, forget it for a few minutes until towards the end of the lecture, and we'll reintroduce it, right? So essentially what I'm trying to point out is, when you're trying to do a match, usually you try to match do a conjugate match. So what this says is gamma in is equal to, in order to get, no reflection, you want, in order to get conjugate matching, you want the source impedance, and therefore the source reflection coefficient to be the conjugate of the source reflection coefficient. So essentially what you've got is gamma S is a formula S11 plus something that depends on gamma L, and likewise gamma L is something that depends on gamma S, right? So that's the reason why we're using the unilateral approximation, because otherwise we've got this coupling which makes our analysis difficult. And what we're doing now is saying, hey, let's begin by making our lives easy. Let's assume S12 is 0. If S12 is 0, then we know that gamma in equals to S11, right? Because S12 is 0 here. This term cancels or disappears. And under those assumptions, let's do some analysis in order to get some intuition. And then what we'll do is later on in the lecture, we'll introduce what actually happens when you've got this coupling. And what I'm going to talk about is also when can you also ignore it, so therefore you can get, you can do the analysis a little bit easier. All right. Now, what I've done here is I've said, let's look at the transducer gain, and we remember our definition of transducer gain, which was the power delivered to the load divided by the power available from the source. And if I've got the unilateral situation where S12 is equal to 0, I can rewrite this transducer gain as follows, which is essentially something which depends on my source impedance, or something which is the gain or the forward gain of the transistor, and also something which relates to the gain of the network associated with the load. So essentially, all I'm doing, nothing special, at least in this very first instance, all I'm doing is saying, hey, let me call this GS, let me call this GO, let me call this GL. That's all I've done. All right. And what I've done now is I've got, essentially, if I look at this, you can actually convince yourself that you've got 3 circles. And what we'll do is we'll go through that in a little bit more detail. So you've got GS, G0, and GL. Now, if you were going to determine the gain in dB, if you've got the product, when you're working in dB, product, it becomes sum, right? So therefore the sum, if you've got product of terms in linear, once you take the log of it, it's the sum of the values in dB. And what we're going to do, all right, so I've got that transducer gain is something associated with the source network, S21 of a transistor, and GL of a load. Now let's consider 2 situations. And the first one is when the transistor is unconditionally stable. All right, and in those circumstances we've got S11 is less than 1, S22 is less than 1, K is greater than 1, delta is less than 1. I just don't know why I'm always mixing it up now. Okay, and then we've got the second case where it's potentially unstable, where either the scattering parameters for the input or output port are greater than 1. Okay, let's now go to the unconditional stable case. And when we look at this, right, we can convince ourselves, and one of the things that I'd like you to do is convince yourselves that the maximum gain under these circumstances occurs when the reflection coefficient of the source or the load is the complex conjugate of S11 or S22. All right, so convince yourselves that the maximum for GS occurs when the source reflection coefficient is equal to the complex conjugate of S11, and also the maximum gain at the load occurs, or GL occurs, when gamma L is equal to S22 conjugate. All right, and if you go through that, you can actually, I think Poser actually goes through the calculation, so you can actually convince yourself that that's the case, right? But it also makes sense intuitively that, maximum power transfer theorem actually tells us, hey, in order to get the maximum power transfer, we need a conjugate match, right? Okay, so convince yourselves, or derive it, or just base it on the fact that we've actually shown this indirectly by, the maximum power transfer theorem. Okay, so under those circumstances, I say, well, let's work out GTU, the maximum transducer gain, and I say that this is the product of these 3 terms, and each one being the maximum, right? So therefore, because you've got a product, right, and they don't depend on each other, you can easily convince yourself that this term on the left is maximized when you maximize each of the components individually, right? So if you had A times B, right, and A and B were positive numbers, and they were all greater than 0, when would you get the maximum? When A was maximum and B was maximum, right? But there you can actually choose an arbitrary large. Here you've got some constraints. But okay, so what I'm saying is we can rewrite this formula. The maximum of the transducer gain occurs when you've got when GS max, when the source, the gain of the source network is maximised, and when the load network is maximised. And we've rewritten this in terms of resubstituting gamma S for S11 conjugate and gamma L for S22 conjugate. And this is what you are left with. Right. Now, what we're going to do is go through and determine the gain circles. All right. So what I've done here is let's normalize, or let's define, and I'll put that thing there so that we can say that that's what we're defining. We're going to define this little GI to be some gain divided by the maximum gain for that particular subnetwork. Right? Why am I doing? You might ask yourself, why is Stan doing this? Right? There's multiple reasons that you might not always want maximum gain. Right? Can anyone tell me of a situation in a transceiver, if you're building a transceiver, when you don't want maximum gain? Think of your TV, right, or your radio. You don't always put it at maximum gain. Sometimes you want it less because it might saturate the wood. You don't always build an amplifier or some kind of circuit to always achieve maximum gain, right? There's something funny happening outside. So, a bear. All right. So essentially, what I'm saying is, you don't always necessarily want maximum gain, and what we'll also see is that under certain circumstances, there are also other benefits of not having maximum gain. For example, the system may be more stable if you actually have less gain, right? And essentially, what we're going to do is we're going to draw the gain circles in order to determine, what are the input and output impedances which give us a particular gain. And what I'm saying here is, let's define something called GI. GI is some desired gain, right, which has to be less than what? Of course, it has to be less than the maximum gain, right? It can be less than or equal to the maximum gain, right? So what I've done here is just said GI divided by GI max, and I've written it in terms of this particular formula. Then what I've done is actually rewrite these in terms of essentially gain circles. And again, Poser does a fantastic job of actually doing the derivation. I use another book by Gonzalez, but notwithstanding that, the point is, if you want to look at the derivation of how to work out the centre and the radius of these gain circles, all I'm saying is, if you want to see the mathematics behind that, just refer to Poser or refer to Gonzalez or whatever in order to actually see the derivation of where you get these, how do you derive the value of the centre and the value of the radius. And GI is essentially the ratio of GI that you want to achieve versus the maximum gain. Okay, so what's our procedure for drawing these gain circles now, right? So we're going to draw a couple of gain circles. Is the bear back? Because a few people are smiling, so no? All right, cool. Let me know. I'm curious to see this bear. All right, so the first thing that we want to do in order to draw these gain circles is to locate S11 or S22 conjugate on the Smith chart, right? And what we'll do is we'll draw that as part of the example. And essentially, reason why we're looking at SII conjugates, and S11 for if we're looking at the source or GS, S22 if we're looking at GL, is because we know that the maximum gain when we've got a stable system occurs when gamma I, let's call it gamma I, is equal to SII conjugate. Right? All I'm saying here is gamma S is equal to S111 conjugate. So this is when the maximum occurs. Okay, that's all I'm saying, right? Nothing special. Okay. And what we can do is we can resubstitute into that, and what we will do is essentially draw the point S11 conjugate on the Smith chart. We draw a line to it, and the point at which we are at S11, we know we achieve the maximum gain for that particular network, sub-network, and that gain is equal to this specific value. Right. Okay. So the next thing we want to do is let's look at some gain circles. So this is actually the point at which maximum gain occurs. What we want to do is look at the gain circles. So what we'll do is we'll look at certain values, right? So usually you choose these values, right? So you can actually choose them to be, 2 dB gain, 3 dB gain, whatever, but some value less than your maximum gain, right? So suppose your maximum gain is 15 dB, you might want to draw your 10 dB circle and your 5 dB circle, right? Or you might want to go 15, 12, 10. You arbitrarily choose these circles, right, depending on what you have in mind or what your design criteria are, right? So there's nothing special about them in an exam or in a test. I'll say, choose GI to be, or choose your gain to be, 2 or 4 or whatever dB, right? But usually as engineers, when you're actually doing your design, you get to choose some of these values which are less than the maximum gain, which are in some way relevant to the design that you're trying to achieve, or the design goals that you're trying to achieve. Okay, then what we do is determine CGI and RGI, which is the center point and the radius for each of these gains, and we plot these circles on the Smith chart. Now let's go through an example, right? So therefore, I'm sure this is as confusing as mud, or as clear as mud. So let's go through an example to actually illustrate what we've been describing or what we've been discussing. So we've got the S parameters. Let's say we've got a bipolar junction transistor, and this bipolar junction transistor is biased in a particular way. It's a 50 ohm system, and what we've got is, how do you call it? We've got S11, S12, S21, S22. We've got all the scattering parameters. Okay. Now you can convince yourself that the system is actually stable. You can do your K test if you want to, if you can so be bothered, or if you so desired, or if you're so asked. And in this particular case, you see that it's an unconditionally stable system. So the first part of it, the first question is, let's calculate the optimal terminations for maximum gain. Okay, can anyone tell me when does maximum gain occur and why? We've said it's when it's conjugately matched. Yeah, all right. So if we know what S11 is, we know the optimal source for a stable system is equal to gamma S equals to S11 conjugate. S11 is equal to 0.73 175 degrees, so S1 conjugate is 0.735 minus 175 degrees. And likewise, for gamma L, we've got S22 conjugate is equal to 0.21 80 degrees. Now, we can draw those 2 points. I think I've only drawn one on the Smith chart. Yeah. So we can draw, let's draw the gain circles for gamma S on this Smith chart. And essentially, all I'm doing, remember the procedure that we've just outlined, was let's draw S11, let's find the points S11 conjugate on the Smith chart, right? So therefore we say it's 0.73, 175 degrees. Like always, we find 175 degrees and we draw a line here. And then we've got to find 0.73. So we identify the length of 0.73 here. And what we do is we start at the origin, we'll start at a perfectly matched condition and draw a line through that to the S11 point, right? And the next question is, what is the impedance for gamma S? Can anyone tell me? How would you work out the impedance? You just read it off the Smith chart, right? So you read, you get, if you read it here, you'll see that it's roughly 0.15, roughly, right? Because this is 0.1, this is 0.2, this is 0.15, so it's 0.1. You can argue it's 0.152 or whatever, right? And what's J? Well, you can read that off also, right? So that's where I'm getting this from, right? So you can just read it. That was the very first thing that we learnt about Smith charts, right? Which was, hey, if you've got a point on the Smith chart, you can easily convert that into an impedance. So that's all I was doing there. Okay, and that gives us our optimal source impedance, and of course we can also work out our load impedance. Now the question is, we want to work out what's the gain of the system at when we're at S11, when we're at S11 conjugate. And what you're able to do is, it's really, all I'm doing is resubstituting into this GS max formula, which we said was just 1 on 1 minus S11 squared. It's equal to 2.14 if you once you do the substitution, or if you convert it into dB, it's 3.31 dB. So all I've done is draw this line, draw this point, and just write the value that I've calculated for gain is 3.31 dB. That's the gain. At that point, for this transistor, when it's because it's stable, the maximum gain of the source network, or the source matching network, is 3.3 dB. But in order to achieve that, I've got to hit that point exactly spot on, right? Which in most cases you won't be able to do, right? It's really hard to get exactly, temperature changes, blah, 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 right? So therefore, it's, but, under ideal conditions, whatever, you can say, well, this is my maximum gain. Okay, then I said to you, then I've asked, what's the total gain of this system? And then all you'll need to do is, you've worked out GS max, and this is away from the Smith chart. We've got GS max, we've got GL max, which is the same thing, and we've got GO, which is the gain of a transistor, which is based on S21. We can actually say that the maximum gain of this amplifier, if we designed the matching network as we've just described, would be 16.47 dB, which isn't bad for a single stage transistor, right? Getting 16 dB gain's pretty good, right? Okay, so the next thing is we have to work out what I suggest. Not we have to work out. I suggest that we work out GS being 210 minus 1 dB, right? And in this particular case, I'm saying I want GS to be a particular gain. That's all I'm saying, right? So that sometimes people get confused and they go, where did you get those numbers? I chose them. I randomly chose them, right? Why did I randomly choose them? Well, let's say, you know, to get my optimal gain's 3 dB, right, for GS. Let's now choose values which are less, which actually shows me which regions and what impedance options do I have available to me in order to achieve that type of gain or those levels of gain, right? That's all I'm doing, right? So I've chosen GS, and you know 2, 1, 0 dB. All of these things have to be done in linear, not dB, right? Don't confuse yourself. All the values have to be. If I give you a value in dB, convert it into linear, right? So therefore I've got GS. Therefore I get my little GS. If you do your calculations, what you're able to do is to work out where the centre and the radius of these gain circles are. Now, the other thing that's worthwhile mentioning in this particular case is that when we're doing the gain circles for these networks, for the source matching network or the load matching network, the centres are always going to lie on this line from S11 to that point 1, right? To the origin. Right? So that gives you an advantage in the sense that once you've drawn that line, when you're trying to identify where the centre is, rather than looking all around the Smith chart to try to identify it, you can say to yourself, well, I'm going to constrain my search space, which is looking at it, because I know that it's going to be on this actual line. I'm actually telling you, you can actually prove it, but you can, in this particular case, take it as a fact, right? Somebody told you that in this particular case, when you're doing gain circles, the actual solution, the centre of these gain circles are going to lie on this line, right? On this line from S11 conjugate to 10, right? That we've drawn, right? So if S11 was down here, what it would mean, it would lie, just for argument's sake, suppose S11 was here, it would lie, all the gain circles would lie on that particular line, right? And I'm trying to distinguish it because that one's pretty close to the straight line across, so I just wanted to make sure that there wasn't any confusion there. Okay, so then what we do is we identify, we know what the magnitude of CGS is. In particular, if we're looking 2 dB, we know we go 0.629, we go through our trick again using our compass, find 0.629, we know where, so we find that location, 0.629, and then what we do, did I get it the right way? Okay, that's why. Just rough, okay. You find that it's roughly about there. I mean, I'm being very rough here. So it's roughly there, so what that gives you your circle, right? The centre of the circle. Then we find the radius, 0.274. We have to go again, find 0.274, and then we draw the circle. That gives us our 2 dB gain circle for GS. We can do our 1 dB and 0 dB gain circles. All right, that's all the gain. What you've done now is determined all your gain circles. Right, for your source, you will do it for your load, for your load also. So therefore, that allows you to understand all source and load impedance values, what level of gain you're actually going to achieve from that system. Okay, clear so far? Good. All right. Now, there's another case that we need to consider, and remember in case number 1, what I said was we were considering what happens when that we had a transistor that was unconditionally stable, right? And as you can imagine, there's going to be circumstances where that transistor may not be unconditionally stable, right? And essentially, if we're looking at a system that's potentially unconditionally stable, what I'm specifically referring to is a situation where S11 is greater than 1. right? The magnitude of S11 is greater than 1. And essentially what does that mean? S1, suppose it was S11 greater than 1. What does that mean? Intuitively. Okay, if it was a passive network, can S11 be greater than 1? No. If it's an active network, obviously it can be greater than 1. But what does that mean, that it's greater than 1? Yes?
It's like there are more power reflectors than
Yeah.
signal.
Yeah, that's it. That's all I'm saying, right? So that's what it means. You're putting in 1 watt, right? And maybe you're getting 2 watts back, right? Because it's an active device, right? The conservation of energy doesn't necessarily. Conservation of energy doesn't apply in the sense that it applies if you consider the rails also in your supply, right? But if you've got a passive network and you put 1 watt in, you can never get more than 1 watt coming back out at you, no matter how badly it was mismatched, right? It'd be maximum 1 watt, right? Because what we're saying here is if you've got an active network, those values can be actually much greater than 1, right? Nothing stops them from being greater than 1, right? So that's essentially all we're saying. We've got an active network, S11 is greater than 1. Let's look at the gain again. And if we look at this gain, and this could be either for the load network or the source network, we can actually see that a critical point occurs when gamma I is equal to 1 on that scattering parameter. Why? What does that mean? What happens to the gain under those circumstances? If I look at this, what happens to the gain? I can just simply substitute in and tell me what happens. All right, 1 minus S times 1 on S is equal to what? 0. Okay, so 1 on 0 is becoming what? Unlimited, yeah. All right, that's why I've said there's a critical point. Okay, good. And what essentially all this is saying, if you really think about it from a circuit perspective, is that the real part of the impedance associated with the reflection coefficients is equal to the negative part of the resistance associated with the scattering parameter. Right. So the scattering parameter, you can think of it as has a negative real part because it's actually an amplifier, right? Or it can have a negative real part. And what we're saying here is that the gamma is actually exactly equal to that, and it's cancelling it, and that's why it's tending to infinity. And in most cases, remember what we said, that in real systems, nothing ever goes to infinity. Generally what happens is you get an oscillation. All right, and essentially what I'm saying is, in order to prevent these oscillations, what we must do is, and this is looking at regions of stability, regions where this system can be stable, is what we want, for example, is the real part of the source impedance to be greater than the real part of the input impedance. This is in order to get stability, or the real part of the load impedance needs to be greater than the real part of the output impedance. Okay? All right. Now let's go through this. So therefore, we'll put it into an example. So therefore, we can actually hopefully appreciate it. Okay. Let's assume we've got this magical FET, or a field effect transistor. It's been biased. It's in a 50 ohm system, and we've taken out our piece of equipment. What kind of equipment would we use to measure scattering parameters again? VNA, yes. And you've used the VNA now? Yes? Yeah. What frequency did you go up to?
3 gigahertz.
3 gigahertz. Okay, awesome. some people are looking a bit blank. Did you use the VNA?
Yeah.
Okay. It doesn't matter whatever frequency. I was just asking what frequency you used it. Like I've got ones in my lab that go up to 110 gig. You can get ones that go up to terahertz. It was just as an example, you know, what did you use it? In this particular case, we're talking about 1 gigahertz, right? So you've plugged in your, you've biased your transistor, you've now connected your vector network analyzer, you've measured the scattering parameters, lo and behold, you've got these scattering parameters. You've measured these scattering parameters at a particular frequency. And then I say to you, well, what's the optimum input and output impedance or in order to terminate this, this network? And I ask a sequence of questions. So let's look at, calculate the optimum input and output impedance. Now we said in this particular case that what we wanted, the optimum impedance, which gives us the maximum value, is equal to the critical value, right? So therefore we know that gamma I is 1 on S11. Gamma 1 is what the input in gamma is 1 on S11. S22 is going to be what? Is it going to be 1 on, or is it going to be S conjugate? And why? Right, it's less than 1, so if it's less than 1, it doesn't have a critical point, so it's just the conjugate. If it's greater than 1, it's 1 on S11, right? Okay. So we've gone through, let's now go through these calculations. All right, so let's look at the input impedance. We know that the optimal input impedance is 1 on S11. That's 2.27, 120 degrees. 1 on S11 conjugate is equal to 0.44, 120 degrees. So therefore we can work out our input impedance. And what we see here, lo and behold, our input impedance is equal to minus 25 minus 23J. So we see that we've got a negative real component. Okay? And then we've also got, like, gamma L is equal to S22 conjugate, and we can actually work out that the impedance of the looking intermittent load is 28 plus 51.5J. Okay, so let's now draw. What I ask you is to draw the unstable region in the Smith chart and construct constant gain circles for, GS equal to 5 dB and GS equal to 3 dB. And what I'm talking about is, I'm asking you to draw these constant gain circles for GS only, right? So the first thing that we would do is we'd put 1 on S11, 1 on S11 conjugate, right? And we would draw essentially the circle, for the gain circle for this, right? So therefore, essentially, all I will be doing is, draw the for the maximum circle, just draw the draw the circle. Okay, all right. And then what we do next, right? After I draw this, and this is essentially for constant given Z, right? What we'll want to do is work out the regions of stability. Who can tell me which region is stable and why on this particular Smith chart? So I've drawn the gain circle here. So right, this is 1 on S11. This is the gain circle, right? And this is 1 on S11. Right. All I've done is I've just drawn the point of maximum gain, and what I've then drawn is the value of this circle, which is of constant resistance. That's the point of maximum gain. Then I'm asking you to tell me which regions are stable and which regions are unstable. And what we've said is, in order for it to be stable, right, what we needed to do was to look at regions where the real the regions where it's stable, here I'm saying the unstable region, but the region where it's stable, we want ZS to be greater than the real part of the input impedance. And that's why I've drawn this circle, right? We've either got, we know the critical region is when the real part of ZS equals the real part of Zin, right? So essentially what it's telling us is anything outside here is the unstable region, anything in here is essentially the stable region. Does that make sense? All right, good. Now, we've got the point S1 on S11 in order to work out our gain circles, and I've asked you to work out what happens for the gains of 5 dB and 3 dB. And what we do is we can work out what GS is for both of these, and then we can work out what RGS is for both of these, and we can also work out where the centre is, right? And essentially, what I want you to then do is to actually draw the appropriate gain circles. All right, so therefore you just go through, continue, draw the gain circles. I haven't actually drawn them here. I've actually just drawn the location of, no, I've actually drawn them here. I've actually drawn my 5 dB circle and my 3 dB circle, right? And essentially what I've done is we would, in order for this system to be stable, what we would do is we'd only use the impedances in here in order to, to build this system. Otherwise, if we went out here, what would happen? The system would be unstable, so we wouldn't implement it that way. Now, the next thing, which may not be entirely obvious, so therefore that's why I put it as a question. If I asked you to tell me on the 3 dB circle, gain circle, where is the point with the that is the most stable? How would you define that, or how would you determine that? It's a little bit unfair because I haven't actually gone through this, but I mean it's. But I thought maybe you'd be able to guess it or look at it, or with a little bit of intuition. Yes?
Is it the one that's closest to the center of the Smith chart?
It's the one with the largest real part, right? Because remember, as the real part goes to 0, the difference between the two real parts goes to 0, you start getting towards instability, right? So therefore, as the real part is larger than the, as the real part becomes larger and larger, the system becomes more and more stable. So therefore, if you were looking at this particular system, and I said to you, well, you want to look at where it's most stable on the 3 dB gain circle, the way that you would identify that is you say which line gives me, the greatest real part. And in this particular case, once you draw your 3 dB gain circle, you'll find this point A has the greatest real part. And what you would do is that is the point which gives you the greatest degree of stability. So therefore, if you were designing your network and you said, well, I want to build an amplifier which has 3 dB gain, but I want it to be the most stable that it can be, but it still give me 3 dB gain, you'd try to get around this particular location or this particular point. Right? How about if I was on the 5 dB circle? Can anyone tell me roughly where they think the most stable point would be? It'd be roughly, I think, if I'm not mistaken, it'd be roughly here, right? Okay. So that also gives you the ability, if you've got an unstable network and you're trying to work out how you should design the gain, or the how should you design it so you still get maximum gain, but you still have maximum stability. This allows you to figure out how to do that, right? If you've got a relatively unstable, yeah.
Could you just go through again like how you determine A? Because the biggest resistive part, isn't it meant to be like close to the infinity?
No, because remember the resistive part is these lines, right?
Yeah.
These are the circles, right? So if I'm in the 3dB, if I go anything here, that's less resistance, less resistance, less resistance.
But so why don't we go further to the right?
Because you can't, because it's the 3dB gain. Oh, you can choose a lower gain.
Like the 30, oh, okay. Yeah, sure. Okay.
All right. So I've said if I'm on my 3dB gain circle, what should be my impedance so that I have the most stable network?
Okay.
And that's all I'm saying is on the 3dB gain circle, if you wanted to achieve 3dB gain from your source impedance matching network, the best that you can do, the most stable point is this point here. If you were at 5dB, it would be, looking at this, it would be here. Now, I don't know, what did we say that the maximum gain was? It was 3dB, right? Was it 3dB or 3.3? No, not of the whole network, but just the source, GS. What was 3.31, I think, wasn't it? Did I get it right? Or, guys, I apologize, I'm getting old. GS. I didn't calculate, or did I calculate it? GL, no, I didn't calculate it. Anyway, if somebody calculates it, let me know. Because it's just one on, so therefore all all you have to do is in GS, you have to substitute 1 on S11 conjugates, and that's 10 into infinity, right? So therefore, because this was GS, this wasn't the actual gain. Anyway, calculate and let me know. But what I'm saying here is if GS is equal to 5 dB, this is the most stable point, and at this particular point where you get the maximum gain, maximal stable gain, you know that a small perturbation, you wouldn't design it there because a small perturbation, you get the resistance a little bit wrong. Small perturbation will get you into a different region, which will make you unstable. That's why you would never design it around this point. So therefore, what you would do is choose it at less than the maximum gain, less than the critical gain. You've got your circle, and then what you would do is choose. In specifically, if you were designing it, you would design it in such a way that you had for that particular gain that you were trying to achieve. You would choose it such that you had the maximum real power, right? Okay, so we've done this, and then what we said is, well, let's work out the total gain in dB if we were on the 3dB circle, and essentially what we said is GL is 1.94 dB, G0 is 16, now 10 log 10 of 16's, I don't know, 12 or something, 12, 13, someone can work that out, and then we're on the GS, we're 3 dB, so therefore that whole network gives us 16.94 dB, right? If we designed it so that GS was, we were on the 3 dB gain circle. Now, when we were describing all of this, I made an assumption, right? In this particular case, because it's a valid assumption because S12 is equal to 0, right? But as I said, in a lot of transistors, real transistors, the reverse isolation is not infinity, right? So but in order to draw the gain circles and to do all this mathematics, we've assumed that S12 was equal to 0, right? That's our assumption, right? So now it's either because it is equal to S12 is equal to 0, or we're saying let's assume S12 is equal